Hi, everybody. We've been talking about reactivity on the periodic table, and we've been talking about the metals, this whole left side of the periodic table. Now we're going to switch over to the far right side, and we're going to talk about these guys right here, which are known as the noble gases or the inert gases. This is group 18 or 8A in that old-fashioned numbering system. And this particular group on the periodic table is separate. It is not in those reactivity trends. As a matter of fact, it is so separate that it is the most non-reactive of all families. So non-reactive that these were not discovered until a little over 100 years ago. A little over 100 years ago, we didn't even know they existed because they're so incredibly inert. And inert means non-reactive. They're colorless, they're odorless, they're tasteless, they are all gases. There was no reason for us to even assume they existed at all. As a matter of fact, helium was first discovered by astronomers looking at the light that was emitted by the sun. And helium the name comes from the Greek word helios, meaning sun, and it was found analyzing the solar spectra, or the light given off by our star. And astronomers said, there's going to be another element discovered, and we found it first in the sun. And then later, scientists here on Earth were taking the air that we breathe, condensing it down into a liquid, separating it into its parts. And when they did that, lo and behold, they found some gases when they separated it out that we didn't know existed. And those were those noble gases. Now, these noble gases get more dense as you go from the top to the bottom. The least dense gas of the group is helium. And you are familiar with helium as a low-density gas because we put it in balloons. It is less dense than air, and because of the fact that helium is less dense than air, it is very handy to put into balloons to make those balloons float. Air is made of about 79% nitrogen and about 21% oxygen, both of which have an atomic mass that is, I think oxygen's about 16, nitrogen's about 14, and helium has an atomic mass of about 4. So it's much, much, much lighter per molecule. And so helium balloons just float, which is really, really cool stuff. If you go to the grocery store or you go to a checkout and there's a barcode on a product, and the checker just slides the product over kind of a barcode reader on the checkout stand, or they're using some sort of a barcode gun, in there are lasers, and those red lasers are helium neon lasers. And those helium neon lasers produce a really pretty red light. So they are useful in lots of different things, not just in kids' balloons. Now, neon, as you go down the group 18 elements, you hear about the neon lights on Broadway or the neon lights in Las Vegas. But neon itself glows this pretty sort of an orange red. But all of the noble gases are used for these lights. You put a gas into a glass tube, and then you hit it with some electricity, and each one is going to glow a different color. So xenon, krypton, argon, helium, even hydrogen. They can combine gases. They can do some other magical tricks by painting the glass on the outside. And so all the noble gases can be used in these absolutely beautiful light shows. Argon. Argon is heavier than air, and it is used very often to protect historical documents. All of the group 18 elements are very, very inert, meaning they do not react with air or paper or anything like that. So the important historical documents, the United States Constitution, Declaration of Independence, they are kept in very protective, careful boxes. And if you put oxygen in those boxes, the oxygen would react with the paper and the ink and the leftover oils from the hands of the founding fathers that touched those papers. And we want to preserve those documents for hundreds and hundreds and thousands of years if possible. So what they've done is extracted all of the oxygen and filled the boxes with argon, this very inert gas that will not chemically react with anything else. And it is a wonderful preserver for historical things. Laser surgery. Argon lasers are used very often. If you have had LASIK surgery or things like that, sometimes an argon laser is used. Sometimes an argon laser is used for welding. Different elements can make different kinds of lasers, and an argon laser is a typical type of laser. As we move down the noble gases to krypton and xenon, krypton and xenon both have a tendency to produce great flash bulbs. The flash bulb that is in your cell phone, most cell phones nowadays have a camera attached, and there's a tiny, tiny, tiny little itty bitty flash bulbs. How do they get a lot of light out of a tiny little package? Well, in there very often is a little puff of xenon gas. And that xenon gas, when it gets excited, it tends to make something that flashes with a very bright light. And that's what you want. If you want a big flash in a very tiny package, you have to find the right element that's going to do that well. And xenon does that very well. Matter of fact, it's also used in landing lights, an aircraft coming through the fog trying to find the runway. It's a good thing. So xenon is used well. The noble gases are so inert that it was not until the 1960s that we first kicked them hard enough chemically to make them react. The first chemical reaction with the noble gases actually involved xenon, and it used the most reactive nonmetal, fluorine, and created xenon tetrafluoride. It was kind of like hitting xenon with something it didn't react with a really big hammer to make it react. So this inert group of gases is useful because the noble gases have shown us what a stable atom looks like. And that is going to become very important in the future of the class as we start talking about why atoms bond. And atoms bond to create stable configurations, like the noble gases. So they're kind of like the model. Everybody else wants to be like a noble gas. Last one at the bottom of the noble gases is radon. Now, radon is a radioactive noble gas. Now remember, radioactivity happens inside the nucleus, and the nucleus has nothing to do with chemistry. It is what's going on in that junky little proton-neutron center, and chemistry happens with the electrons on the outside. Radon can be a problem because depending upon where a person's house is located, if there are rocks and soil around the home that naturally decompose, giving off radon gas, the radon gas can seep in through cracks, crevices, drainage, get into the home, and then radon is heavier than air. It sinks. So it's not going to get up into your attic. It's not going to get up into your first floor, but it has a tendency to pool in the lower levels, like your basement. What happens is that can be dangerous if there's a lot of time spent in those lower levels of your home. If you just go down there once a week to throw in a couple loads of laundry, not a problem. But if you're sleeping down there, if there's an apartment down there and somebody is living in it all the time, that can be a challenge. You can buy a Radon Test Kit at most superstores. The test kits are under $100. And you hang the test kit, there's instructions, but you hang it in the space you want to test for a period of time, and then you mail it off. They analyze how much radiation it's been exposed to, and they let you know if your basement is okay and safe from radon, or if it's something you should worry about. depending upon the part of the country you live in. It can be a challenge or it cannot be. I live here in Wisconsin, and the problem with Wisconsin is we've had the glaciers have marched through our state many, many times. So it all depends upon where you lived and what kind of rocks got dumped by the glaciers. So it's never a bad idea to test your home, and then you know for sure. Now, we're going to continue with reactivity trends, but we've been talking right now about those noble gases, and they are the most non-reactive of all families, and so they are not in the reactivity trends for metals or non-metals. They are their own separate entity because noble gases just plain don't want to react at all. See you later. Bye-bye.